Welcome again, betas, to a new lesson. Today we'll talk about rotations, but more importantly, we are going to introduce a concept which is covariant versus contravariant objects. In the first video of this series on general relativity, I told you that in general relativity we use lower indices and also upper indices. However, in all these lessons we have been using only lower indices. The reason is that we are working in flat Euclidean 3D space, so we really didn't care much. However, I think that it's important to remark the difference between covariant and contravariant at this point in the course. And the best way to do this is because covariant objects, they transform differently under rotations in comparison with contravariant objects. So both things, they transform differently. So we may identify covariant objects with lower indices and contravariant objects with upper indices. We'll talk more about covariant and contravariant in the next two lessons, but you can stick with this information just for this video. And you can also think about another object, for example, which has 2 upper indices and 3 lower indices, and this will be an object which is 2 times contravariant and 3 times covariant, and this is a tensor, but we'll talk about tensors in later lessons. So we are going to work with frames of reference. So let's say that we have this frame of reference and the x and y axis, and we have a vector. I'm going to paint it red. Okay, we have this vector v. Let's say that the one in this reference frame is Alice, and now we have our friend Bob, who is in another reference frame, and both frames of reference, they have the same origin, but their axes have different orientations. Okay, the axes are also perpendicular, as in Alice frames of reference, but the orientation is different. So this is Bob frames of reference. When Alice and Bob, they inspect the vector, Alice might say, okay, so the vector, it has some Vx component and also some Vi component. However, Bob might say, no, the vector, it only has Vx component. It doesn't have any height. It's only in the x direction. So they do not agree on the coordinates of the vector. However, they agree on one thing, which is the length of the vector. Okay, no matter the frame of reference, the length of the vector is going to be always invariant in 3D space. We are in flat Euclidean 3D space. We'll see that in special relativity, the length of the distance between objects, such as a rigid rod, it doesn't stay the same, but we'll see that later in the second unit. But for our purposes here, the length of vectors, no matter the frames of reference, it's always the same. So the length that Alice is going to measure is this one, and it's going to be the same as the length that Bob measures. We can get rid of the square roots, and we arrive at this equality. So from this equality, we can think about a general rule of transformation between the x, y, and the x prime, y prime coordinates. So we want a translation between Alice's reference frame and Bob's reference frame. We can see that the most general transformation is simply this one with cosines and sines. This is for the Vx prime coordinate, and for the Vy prime coordinate, okay, you can check that this works. We're going to write this into matrix notation, where the vector components are going to be column vectors, and we are going to find a new matrix. So this matrix right here, which is formed by cosines, and sines, is what we are going to call the rotation matrix. Okay, this is going to be the matrix R. Now that we have encountered a matrix, we're going to like a little break to explain matrix multiplication and how we can express it in index notation. So let's say that we have a column vector A, which has components A1, A2, dot dot dot, and we have a matrix M whose components are M11, M12, dot dot dot, M21, M22, dot dot dot, dot dot dot. So you may have noticed that I'm writing the vector components as upper indices. So yeah, the vector components are contravariant objects. So be careful, because we have been writing in all these past lessons all the vector components with lower indices, but they are really contravariant objects. So from this video and in all the rest of the course, we are going to write the vector components as upper indices. And here the matrix components, we are going to write them as an upper index and a lower index. You will see then why is it the case. But just take into account that the first index, no matter if it's up or down, it accounts for the row of the matrix. It's the row number. And for the second index, no matter if it's up or down, it accounts for the column of the matrix component. Okay, so taking this into account, we are going to multiply M by A, and we are going to find a formula for index notation. You can see that if we do this, we find M11A1 plus M12A2. If we had written more components, we will have find M13A3 dot dot dot. Here we have the same, but instead of a 1 here, we're going to have a 2. So let me just copy this. This is the same, but with a 2. And now it's the same, but in the upper index, we're going to have a 3, 4, 5, and the number of components that we have in our vector. So you might write this simply as, let me do some space here. We may write this simply as M1 and now I AI, M2 I AI. Remember the Einstein summation convention. When we have any two repeat indices, they are summing together. In this case, I starts from 1, 2, 3, and whenever the components the vector A has. Now we have M3 I AI and dot dot dot. Okay, so taking this into account, if we have named, let me raise this arrow, if we have named this matrix R, we may write this as R1 I, and now we are going to treat the vectors. Vx is going to be V1, Vy is going to be V2, and from the prime components, V prime x is going to be V prime 1, and V prime y is going to be V prime 2. So this is just R1i Vi, R2i Vi, and then with this notation we can write that V prime j equals Rj I Vi. So this is a very important formula, because with this formula we have found that given any vector v with no matter how many components, if you want to translate this vector, which is in Alice's reference frame, if you want to translate this into Bob's reference frame, we have to do a matrix multiplication, and this in index notation is expressed with this transformation. So in order to transform a vector v into another frame of reference v prime, we just putting here the R, we contract the closest indices, and the transformation is done. So now you may notice why we wrote the first index of the matrix as an upper index and not lower index, because vectors, the vector components, they have upper indices. So if we contract these two indices together, this is an upper index. So in the first slot, we couldn't have a lower index. You can have an equation, let's say for example, AI equals MIK VK. Because these indices, this is an upper index and this is a lower index. And they are free indices. So they have to match. Okay? If we have some free indices in an equation, if the free index is an upper index, the other side of the equation must have the same index as an upper index. So they need to match. That's why we express the rotation matrix with one upper index and one lower index. We have done this for the I index running from 1 to 2, but we could have done it also for the index running from 1 to 3, from 1 to 4. So, well, of course, in that case, the R matrix will have changed. So let's see, for example, in 3 dimensions, the rotation matrix will be of this kind. So in 3 dimensions, we have like the z axis, but we haven't done nothing in the z axis, so it remains invariant. So if we write here a z coordinate, it's going to be multiplied by 1, and these coordinates don't matter because they are zeros, so it remains unchanged. So this will be the rotation matrix in 3 coordinates. Now that we know how contravariant objects transform under rotations, which is just this expression, we want to know how covariant objects transform under rotations. So we are going to do a trick, okay, which is using the Kronecker delta. We are going to multiply this equation by the Kronecker delta Kj. Okay, so we are going to have this thing. And now the Kronecker delta, it collapses indices. So it's going to kill the J index and it's going to place the K index. But the K index, it's a lower index. So this is basically V prime K with lower index. So now we are like finding the components of a covariant object. In this case, we are going to have, well, let me just write here an arrow. Here we're going to have like the same thing. We have the Kronecker delta, it's going to kill the J index and it's going to place the K index. Okay, now you might think that we have finished, but this isn't the case. Because in our original transformation, we have as an input a contravariant object and as an output another contravariant object. However, here we have as an input something which is contravariant and as an output something which is covariant. So this isn't really a covariant transformation law because here we have something contravariant. So we need to transform also the v vector, well, these contravariant coordinates. So we are going to use again the Kronecker delta, okay, and you can check that this is indeed vi because it collapses the repeat index j and it places in the upper I. And now simply we can use the Kronecker delta, we can apply it to the R matrix. And this is simply Kj Vj. So we have found our transformation law, which is simply V prime j equals Rk, well, Rj I Vi. We have arrived at the transformation law for covariant objects. I've decided to cut the video because it was getting too long, and in the next lesson we'll see what's the meaning about the rotation matrix with the swapped indices, and see you there. Bye.